Okay, so let's do in class 13. So it says verify Stokes' theorem when f equals negative y cubed I plus x cubed j minus z cubed k, and S is the intersection of the cylinder x squared plus y squared less than or equal to 1 and the plane x plus y plus z equals 1. Let's first draw the cylinder. So here's a cylinder. So pretty much the x squared plus y squared is a less than or equal to 1 is a circle. So it's basically unit circles going all the way up, and z is free, so it's going to be unit circles all the way up to infinity here and down here. Now I'm going to intersect this with this plane over here. So this is just an equation of a plane, so let me draw that now. Let me first point out that ax plus by plus cz equal d is a general equation of a plane. So this guy up here is a plane. Okay, so if I graphed it then, or graphed it would look something like this. Okay, now it's going to be cutting our cylinder, so imagine the plane intersecting, cutting the cylinder at an angle here. And that intersection will be our surface, so let me draw what that would look like. So my answer would look like this then. And it's pretty much an ellipse. If the plane had it cut it straight on, it would have been a circle, but it's cutting it at an angle, so it's going to make an ellipse in here. Okay, so we have to now parametrize this S as our next step. So let's see how we can do that. Let's first parametrize our x squared plus y squared less than or equal to 1. So to do that, you can let x be v cosine u and y be v sine u. And since it's less than or equal to 1, the v is going to range between 0 and 1, and the u value will be from 0 to 2 pi. So we have this, so v goes between 0 and 1, and then the angle would go between 0 and 2 pi. But now we haven't found a z value yet, but notice up here in the plane, so up here, we can solve that for z, so let's do that. So I've taken my plane up here, brought down here, and solved it for z. So I subtracted x, subtracted y. See if z then equals 1 minus x minus y, but x now is equal to r cosine, v cosine u, and y is equal to v sine u. So we can make those substitutions for these. So let's do that. So making those substitutions, so again, in place of x, I'm going to write v cosine u here. In place of y down here, I'm going to write v sine u. So I did that here. So that would be my z value. Okay, so let's write now our parameterization of our S. So here would be my parameterization of S. It would be v cosine u for the x value, v sine u for the y, 1 minus v cosine u minus v sine u for the z. So have your x, y, and z. So let's draw now the D region. So here's our D region. The u goes from 0 to 2 pi because it's the angle, and the v goes from 0 to 1. So this would map this rectangle in the UV plane onto our region S over here. Okay, so now let's state Stokes' theorem and we'll start verifying it. So here's Stokes' theorem here. So again, it states that the work done by F going around the boundary, so the boundary in our case would be there, going around the boundary. So the work done by F going around the boundary equals the flux of the curl of F across S. So here's our S in here. So let's look at, we're going to look at this side first. So let's compute that side first, then we'll come back and do the work guy, the line integral part later. So let's work on this guy first. So let me erase a few things. Okay, so here's what we have, summarizing. We have our R parameterization up here, our F, our D over here, and then our flux across curl of F. is equal to this we've shown in 15.6 over d, where d is a region over here. So let's start computing the partial derivatives of r with respect to u and v. Let's do that first, and then we'll do this cross product. Okay, so and then we'll have to find the curl also. So let's first find the partial derivatives. Okay, so let's do r derivative with respect to u. So here's my r up here. So derivative of the first component with respect to u would be minus v sine u, because derivative of cosine is minus sine. Then derivative of the second component with respect to u would be v cosine u. And minus derivative of this guy will be minus sine, because of minus in front also be plus, then v sine u, and then minus v cosine u. So that's that guy taken care of. Let's do rv next. Oh, sorry, this shouldn't be here. Derivative 1, 0. Messed up there. So let's do rv next. So for rv, derivative first guy respective u just be cosine of u, and derivative will be just sine of u, and derivative this one would be, so it'd be derivative of 1 would be 0, derivative of this guy would be just minus, be minus cosine u minus sine u. Okay, so let's do the cross product now. So ru cross rv. So cross product would look like this. Okay, so I have my ru and then my rv down here. So let's start doing it. So we'll do the I component first. So that will be equal to here, this times that. So it will be, pull a minus out in front, minus v cosine of u times cosine of u plus sine u dot times that, then minus that times that, so then minus, we can pull a v out of that actually, as pull the v in front here, v sine u times sine u minus cosine u. This is all in the I direction. Okay, let's do the j one next. Okay, so doing the j one next. So covering the j column will be this, the minus sign in front. This times that, 2 minus will be plus, will be v sine u times cosine u plus sine u. And this times that minus. The minus then, I'm going to pull a v out of this one too. I'll put it in front here, v cosine u times sine u minus cosine u. This will be all in the j direction. Okay, let's do the k1 now. So doing the k1, this times that, have here, this times that, have here, you can check. Okay, now let's simplify this. So in the I component, I'm going to pull out the minus v in front, then start multiplying things in, so it'll be that times that'll be cosine squared there. Then going through and doing the rest over here. So this trippy thing you can check, like a cosine squared, and you get a cosine sine, then a sine squared, and minus sine cosine. So these two will cancel here. And cosine squared and sine squared is 1, so it's just going to be negative vi here. Let's do the same thing with the j now. Let's factor a minus v out. Okay, so I factored the v out. So then it's to be a minus in that one. So then multiply stuff in. That'll be sine cosine here, sine squared here. That'll be minus sine cosine, and then plus cosine squared. So these two cancel. And again, sine squared, cosine squared is 1. So this also gives us minus v. And lastly, let's look at the k1. I can pull a negative v out. So pulling a negative v out, and then I'll have a cosine squared, sine squared. So this will be negative vk. So our answer then becomes negative vi minus vj minus vk. Alright, so let's keep going. So let me erase a few things here. So I have my RU cross RV in the corner over here. Okay, so now let's do the curl of f next. So here's our definition of curls. Is basically the del operator crossed with our f up here. So that's how I got the components down here. It's negative y cubed x cubed minus z cubed. Okay, so let's start doing this. So doing the I component would be the partial y operator acting on negative z cubed, which I have here, minus partial z operator acting on z cubed, which I have here. We'll come back to that now in a second. And then it'll be minus, doing the j one now. So doing the j1 will be partial x operator acting on negative z cubed, which I have here, then minus partial z operator acting on negative y cubed, which I have here. And lastly, let's do the k1. So for the k1, we'll have partial x operator acting on x cubed minus partial y operator acting on minus y cubed. Okay, so let's work these out then. So looking at the I component, partial y operator acting on z would be 0. So it'd be 0 here. Partial z operator acting on x would be also 0. So basically you'd have 0 in the I. Then moving to j, partial x guy acting on z would be 0. So minus 0. And partial z operator acting on y would also be 0. So it'd just be 0j. And then over here, partial x operator acting on x cubed would be 3x squared. And then double minus there will be then 2 minus will be plus. So the partial y operator acting on y cubed would be 3y squared. I guess we can factor out the 3. So it'd be 3x squared y squared k. So that's our curl. Okay, so let's keep going. Okay, so we've got everything we need now. So I have my curl down here. We've got everything we need now to start doing the double integral. So let's see. So it's equal to integral over d. So d here, we're doing u first. So it's going to be, so u goes from 0 to 2 pi on the inner one. V goes from 0 to 1 on the other one. Then we'll have the curl of composed with r of uv. So here's my r up here, and here's my curl over here. So it's going to be 0i plus 0j plus 3 times. So in place of x, now I'm going to put v cosine squared plus y squared. So plus y is v sine u. So it'll be v sine u squared k dotted with our ru cross rv, which is right here. So it'll be dotted with minus vi minus vj minus vk. Okay, so now let me erase my ru cross rv and my curl in my way. So let me just erase those for now. So look at this. I have my du dv at the end. So let's do this dot product now. So I'm multiplying negative v times 0 be 0, negative vj times 0 be 0, and negative v times this guy. So let's do that. So doing the dot product, we get this. So I squared the v squared, and I pulled it out because I has v in both of those. So squaring it and pulling it out. And I have a cosine squared here, sine squared here, which would be 1. So this whole thing becomes then, just becomes this then. So negative 3v cubed double integral. So we're integrating with respect to u first. So we're treating v as a constant. So we're just going to tack on a u here. So let's do that. So integrating, we get negative 3v cubed u evaluated at 2 pi and 0. So then putting 2 pi in place of u, we get, So we get the negative 3v cubed times 2 pi. I'm going to pull out the 2 pi and the minus 3 as a minus 6 pi in the front like I did here. Then I have to integrate the v cubed now, so let's keep going. So integrating v cubed, we get v to the 4th over 4. Then I'm going to evaluate at 1 and 0. So this will just be then, so putting 1 in, it'll just be 6 pi over 4. Which reduces to, sorry, should be negative here, I lost my minus sign. Which reduces to negative 3 pi over 2. Crossing a 2 off there. Okay, so this is the flux of the curl over our surface S we found was negative 3 pi over 2. So we did one side of Stokes' theorem. We still have to show it equals the line integral part of it around the boundary, but I'm going to do that in another video. So we'll do part 2 to this video since it's kind of long, this video already. So let's leave it there. We'll do part 2 to this. We'll do the line integral in part 2.